Assembly drawings. Now, don't freak out when you hear assembly drawings, because I've noticed sometimes in the past, previous students tell the new students that everything is fine until assembly drawings. So you don't have to believe what they tell you. Um, an assembly drawing is basically just an orthographic drawing, like we've done up to now, just of more than one thing at the same time. Usually rather basic components, so less complicated than all of these fancy auxiliary view components. Okay, good. So up to this point, we did detailed drawings, which are used to describe the shape of a component, describe the sizes, meaning you can add dimensions to it, and other explanatory notes like material, surface finish, heat treatment, and so on can also be added on a detailed drawing. Many of those we did not do in NGC. And then you also gave it a descriptive title. So, an assembly drawing does not contain all these points 1 to 4. It contains a picture that shows the relationship of different parts to each other, and it basically shows how parts fit together. And then we also have a part list. So it's just a little table that describes all the names of the parts and shows where they are located in the assembly. So for detailed drawings, it's an orthographic drawing of a single component containing all of the dimensions. If needed, you can show surface finishes and the material to be used, meaning the component can actually be manufactured just from having that paper in front of you. You can make a component exactly like the one specified, exactly to the right smoothness where it needs to be smooth, roughness where it needs to be rough, the material, the size, the tolerances, everything from the detailed drawing. Assembly drawings do not contain so much detailed information. So an assembly drawing just shows you how these components actually fit together. So in the overall production of products, you have materials coming in, then detailed drawings tell the manufacturing plant how to shape those materials into the components that your assembly will comprise of. The assembly drawing is then given to the assembly part of the production chain, where it just shows how the components are put together. You can even have multiple manufacturing facilities sending components to one assembly plant. An example of that is the typical motor car. You can have a company like Gearmax that manufactures rear axles and differentials and sometimes smaller gearboxes. So they ship the gearboxes to Toyota South Africa, which then puts them in their bakkies. So that would be manufacturing plant A. Then plant B could do the bull bars, and plant C could do the lighting and body panels and whatever. And then you have one assembly plant like the BMW plant here in Pretoria, where all of these different manufacturing plant outputs gets put together to form your 3 Series BMW. Just wanted to check that there aren't any questions. So, what is an assembly drawing? It is an orthographic drawing with sections where needed to indicate the relative positions of different components with respect to each other. Usually 2 or more views will be present. A part list is included where materials, quantities, and part names or references to part drawings can be given. This is just an example of a small assembly drawing. The 3D color picture there is just as a reference. In assemblies, we will not ever make use of isometric drawings. So the drawings that you guys draw, You will never do an isometric assembly drawing. It just gets too complicated and it's kind of pointless. So in assembly drawing, we do not add all of the dimensions needed to create the individual parts. Remember now, the detailed drawing for each part has already been made before you can even get that part in your hands. So an assembly drawing is at a later stage in the whole production layout. So you will not need to know the exact details or dimensions of each component in an assembly drawing. You just want to show how they get put together. So you won't need to know the surface tolerances and all of that. So in assembly drawings, we will have three types of dimensions. The first type is a functional dimension. So that is a dimension that you need to have in order for you to be able to use the product, whatever the product might be. So if it is a bicycle, for example, a functional dimension would be the radius of the crank arm where the pedals are, so that you know how high your legs will move up and down when you pedal the bicycle. That would be a functional dimension. Another functional dimension for a bicycle would be the diameter of the wheel. Small diameter wheels take up less space, but they also get stuck into ruts and grooves more easily. And larger wheels have better stability at speed as well. So a functional dimension on a bicycle would be the diameter of the wheel. It could also be the height of the seat from the ground. That is functional. You need to know that height for you to be able to use that bicycle. If the height is not set right, then you won't fit on the bicycle. You will either have to stand or you'll have some other sharp device poking your back the whole time. So that was functional dimensions. Overall dimension is basically like a packaging dimension. How big of a box do I need to be able to put this assembly inside of? So that would be your total height, total width, and total depth after it is assembled. And the third type of dimension we're going to look at for assembly drawing is your mounting dimension. So if this assembly has to be mounted to some or other structure, what is the size of the hole and the spacing of the holes, so that I know that I can prepare my mating surface that these two would actually fit together. So those are the only three kinds of dimensions. You won't show web thicknesses and that kind of thing in an assembly drawing. Again, that same example of this little wheel. So a mounting dimension is the dimension of these holes. So the diameter of the hole and the spacing between them. This is what I would need to know that I can prepare a surface where this assembly is attached. The second type was your overall dimension. So that would be your total height, total width, and total depth. Third type of dimension was our functional dimension. So a functional dimension is what I need to know to be able to use this thing. Usually, you need to know some more information about the application of the assembly. This assembly is a rope wheel. So it's a wheel that is used to guide a rope. Then a functional dimension would be the diameter of the rope, so that you know, is this thing made for fishing line or is it made for a very, very thick rope like the ropes they use to anchor big ships. So that's an important thing with respect to the function of the assembly. Another important thing in this one's case would be the diameter of the wheel, which was actually given as an overall dimension already. So that overall dimension there, the 328, is actually a overall and a functional dimension. Okay, cool. Now the question of hidden detail in assembly drawings. Typically, we don't want to add hidden detail in assembly drawings because it will most likely just cause the drawing to become so complicated that it's hard to understand what is what. So usually we do not add hidden detail in our assemblies unless it is needed for clarity. Okay, we'll get to some examples of that at a later stage. Section views in assembly drawing. Sections are commonly used in assembly drawing, and it allows you basically to show what is going on the inside of this product, which has multiple things going on the inside. You'll remember from our sections lecture, I told you that we can use different hatching patterns to distinguish between different components. If you page back, you'll remember that the example we had there was the conrod or connecting rod example, where we had different hatching directions on the left and right hand side of the little partial section, because it allowed us to show that it's two separate components. So remember, with hatching, a component is hatched consistently throughout the whole component. So component A is one component, and this one over here, which was also labeled A, just because of the angle. So this one at the bottom is a different component. It's two separate pieces of material. So we can hatch it in a different direction. Then this different direction hatching would actually show us that the one at the top and the one at the bottom are different. Okay, so hatching can be used to show or indicate different components. You'll notice there number B. B is basically a thin component in between these two thicker ones. Now, doing hatching on something that small is very impractical. It will be hard to actually see the hatching. So, thin components in a section view may actually be colored in. So that's why we colored it in over there. It's because it was so thin that hatching isn't very clear to do in that very small region. Next thing is standard components like your bolts and nuts, washers, keys, those kind of thing. Because they are standard, there's not really a point in it for us to make a section of it. It's like telling someone something they already know. You know what's inside of a bolt? In the bolt, there's just solid material. In the nut, there is a thread. We know what it is, so we don't have to show it. So standard components are not hatched or sectioned, and these include bolts, nuts, pins, and keys. There is one exception to that though, and that is a circlip. Circlips are hatched. Let me quickly show you why. Focus okay there. Okay, so okay, so here we have a shaft with a circlip on it. Now, if I just look at it like that, this looks like it could be a shaft with a little step machined into it, meaning it could look like that step is part of the shaft, which in this case it actually does look like that. So that's why when we make a section view of a shaft with a circlip on it, we hatch the circlip, then we can show, okay, this shaft has a groove in it, and there's a circlip in the groove. Okay, so circlips are hatched. If it is small on your drawing, you'll notice this one I do very big. So let's say it is quite small on your drawing. Now obviously to do hatching on a block that is that small is very hard. And this is now that same example. If the hatching becomes too small, you can just color it in. But if it is hatchable, then you do hatch it. Okay, so standard components are not cut except for circlips. Usually, shafts and other relatively solid components are not cut open either. If we have a long shaft, and I now make a section through the middle of this shaft. This is a solid shaft. So if I now go and hatch the entire shaft, I haven't really shown anything more than what I would have if I had not hatched it. Okay, so if it's a very solid component, then you are actually allowed to skip the hatching because there's nothing to show. Okay, if there was some other keyway into the shaft, then you could always go and just make a little broken out section to show where there is internal detail, and the rest of the solid shaft you leave unhatched. So this is the partial section that I just did. Then item numbers. Remember earlier I said in an assembly drawing we will have the drawing that shows how the parts fit together and a list of all the parts. Now we need to also be able to indicate which part is which. So from the list item, where is that on my drawing? So the example this stuff takes long to draw. Okay. Bolt, nut, bottom plate, top plate. So when we want to refer to a surface, you can color a dot in on the surface, bring the line out, make a small horizontal portion, make a circle, or we call that a balloon. Make a balloon with a number in it. So that is the correct way to do it. If you don't want to refer to a surface, let's say it's too small to put the big dot on it, you can make use of an arrow and put the number in the balloon with the short horizontal portion. The horizontal portion, however, is not a specific requirement. You could always draw from the balloon straight to the surface with an arrow if you're pointing on the edge, or a dot if you're referring to a surface. Okay, so all of these balloons are perfectly fine. Now please note though that the horizontal portion of the line is about the same size as the diameter of the balloon. Going at an angle for short distance and a long distance horizontally is not correct. So you will lose marks if you do it that way. We've noticed many times that people try to get these balloons to line up, which they are supposed to, but then they make use of these long horizontal lines. It is very bad practice to do that because then it starts to look like parts of the assembly. So don't do that. Another thing, where these balloons are close to each other, please make sure that they are in line with each other. So where they are close, make sure they line up. They can line up vertically or horizontally. And it's not all of the balloons of the entire assembly drawing that have to line up, just where they are close to each other. It just makes it look a lot neater. Okay, that's a good question. Yes, you are allowed to use dots and arrows interchangeably for any part. So it doesn't matter how you do it, as long as when you refer to an edge, you use arrow, and the surface you use a dot. I'm not sure why you say you must make the balloons bigger, but okay, big enough on the drawing is fine. You can actually mix and match with the balloon style. Personally, I actually prefer just the straight one, just because it's less effort than making the horizontal one. So for MGC, I think initially you had to do it like this, but then I brought the rule in that says if you do it like that, it's also fine. Just don't do it with the long horizontal one. Okay, can the balloons extend vertically? Well, yes. Just one other thing also is these balloon lines. Always try to make them at an angle. So never have a balloon straight horizontally or straight up vertically as well. Don't do that. The reason being, then your balloons might actually, same reason as these long ones, start to look like lines in your drawing itself, which they aren't. So if you purposely make them at an angle, then it's easier to distinguish that they are not the parts, they are just balloon numbers. The balloon lines don't cross each other. Okay, so on the left hand side we have the correct numbering. On the right hand side there are a couple of mistakes. Firstly, 3, 4 and 5 are close to each other, so if possible make them line up. You'll notice also 3 almost looks horizontal, so if possible rather move it that it is not perfectly horizontal but rather at an angle. Number 1 has a super long horizontal line, which is not right, and number 1 refers to the same part as 2. So make sure when you number them that you don't number the same thing twice and skip another one. So the balloons can line up both horizontally and vertically. It doesn't matter. It's basically just when you have balloons close to each other, make sure that they are neatly aligned, either vertically or horizontally. So this is the part list. Now, on your drawing sheet, you'll remember that your drawing sheet has a border around it, and at the bottom right of the drawing sheet there is your title block. And you'll notice now, if you look at the title block, the top line of the title block the first one is called item number. The second one is called quantity. Then there's a material and some other part number or something at the end. So when you do a part list in an assembly drawing, make sure that it lines up with the one on your drawing sheet. You can just freehand then extend from there upwards. And then start to add your item numbers. We start numbering at the bottom. So we number from bottom to top. And there's a very good reason why we number from bottom to top. As I'm completing this table, if I want to add another component, I just add one digit higher and add the row. So adding number 7 over there was very easy. And so on. If I started numbering at the top, then when I wanted to add number 7 and number 8, I would have ran into a serious problem over there. So we always number from the bottom to the top. Just makes it easier for us. When you do this on a computer, it will automatically redo the entire table every time you add a component, so that's very easy to do. But when doing this by hand, we number from bottom to top. So start numbering from the bottom to the top. Then a good practice, although it's not a rule and you won't at all be penalized for it, is to start numbering the major components first, like the big ones, and then the small components last. So when you do numbers to parts, you basically just start with the biggest component, give it a name, give it number 1 obviously, and then as you do the next component it will automatically be number 2 and 3 and so on. Okay, materials we will do a bit later. This is a very good question. We fill in the entire title block using our pencil, because then if you want to erase something, it is easily done. Okay, so remember this example with item 1, 2, 3, and 4. Let's be a bit fancy over here. So I put 2 of number 2 there. So now I'll have my title block. Okay, so from here upwards, now remember that this title block is always at the bottom right of your drawing sheet. So you must plan the location of your assembly drawing such that you leave enough space to put the title block in there. Okay, 1, 2, 3, 4. Number 1, I have one of them. There's one of number 1. Description, this is a bolt. Material, I'm going to skip for today. You can just write steel if you want. Number 2, there's 2 of them. Not M20. Number 3, one of them. Number 4, one of them. These names will not be specifically given. You will have to assign a sensible name to every part. Yes, thanks, Keegan. Just to re-emphasize again, I use a pen in the drawings so that it's easier to see on the screen. In MGC, the only thing you do in pen is write your name on the drawing. So if you have two bolts and they are the same bolt, like the two nuts in this example, you only have to indicate one of them. Yes, it's M20. M designates that it's a metric screw thread, and the 20 is the nominal diameter of the thread. So the 20 is basically that size there. Okay, cool. Back to the lecture. So, how to assemble an object. Now that we have a basic idea of assemblies, now the question is, how do you actually figure out what goes where? First thing to do is look at the object's name. Many times the name can describe the function of the assembly, which will also assist you with how the thing should look in the end. Then we look for logical orientation of parts. For example, a car has its wheels at the bottom, except for the steering wheel, which is somewhere in the middle, or except if it's a Hilux as well, because then their wheels go to the top quite easily. But most importantly, when trying to figure out how these things get put together, is to look at the dimensions. So the dimensions will tell you which components can possibly fit together and which ones can definitely not. For example, if you have a hole with a diameter of 29, then a 30mm shaft will not fit in there. Remember, we are assuming most of these components are metal. So this is not even an interference fit. Remember, with interference fits, the decimal value that this one is bigger than that one is literally like 50 micrometers, not a whole millimeter. So a 30 shaft will never fit into a 29 hole. So when trying to assemble your stuff, look if the dimensions actually make sense. If it was a 30 shaft and a 30 hole, then yes, it could fit, but not with a 29. Okay, cross-threading, I didn't specifically mention that, but cross-threading is basically when you try to screw a bolt into a nut, but you don't let the two spirals match up properly. So basically, you screw it in at the wrong angle, and then you force the bolt to basically press a new spiral shape into the nut. So it's effectively stripping the nut. You are basically deforming it permanently. Yes, the Hilux does do that quite easily. No, they don't always crash. They sometimes park as well. So stripping is one thing. Cross-threading is basically, as I said, when you start them wrong. You can quite easily see it on a plastic bottle. So plastic bottle, if you take the cap and you screw it on correctly, it goes on quite easily. Okay? If you now go and start it at an angle, you can sometimes get them that they would actually go, but then it goes at an angle. And then as you want to tighten it, you can't just do it easily like that. You have to really take it and apply a big force. So that's actually cross-threading. So as I said, most important thing for assembly is look at the dimensions. I just want to check the last questions. Okay. Assembly of parts is quite often an iterative process. This means that you will definitely identify potential part locations and then imagine what the assembly would have looked like if the parts were inserted in that way. Then you will analyze your assumption based on what makes the most functional sense to have the part in that location, assuming obviously that the dimensions would allow it to go there. Quite often, there is more than one way to get the correct answer. So if you review any of my examples and I assembled it in a different sequence to what you would have, don't worry. Many times with assembly, you can assemble it in different sequences, but the final product should still look the same. Another topic is it might happen that an assembly problem has more than one possible assembly layout. In this case, it is important to look for additional clues as to which is the correct one. This can be given in the descriptive name, the assembly's application, or other additional comments in the question's assignment's question. So I might, for example, give you a schematic that says this is where it should go. Make sure you read and understand the entire problem at hand before just jumping in and answering the problem. And plan before you start drawing. I would even recommend that you guys go and on your drawing sheet, there's the title block, maybe pick somewhere in the top and just do a brief planning to show where your view layout or how your view layout should be. And then you can also plan for the title block to be in place. So make sure that there's enough space in your planning already. You can send Mr. Isaac Sitsedi an email on the CAD assignment. He set it up. Okay, then we can quickly just page through this DIY car assembly exercise. I usually recommend that you start with the biggest component first, because usually most of the other parts will be attached to the biggest component. So we start with this plank or chassis of the vehicle. And you'll notice it's got all of these little grooves and holes in it. Then check the diameter and spacing of the holes to see if you can't find something that has the same size hole and same spacing between them. In this example, the axle support plate actually has the same hole spacing and sizes. That corresponds to there, 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 and there. Then you can use your fasteners to actually put the support plate in place. There is the chassis something like that. So you put the bolt in from the bottom in this case, or from the top, doesn't really matter in this example. Put it through the support plate, through the chassis, and put a nut on the other side to basically compress everything together and keep it nice and tight. Do the same on all four corners. Then we look at the diameter of the hole in the axle support plate. Look at the diameter of the hole in the wheel and the pulley and find that all of those are equal to the shaft's diameter. So you can insert the shaft through the pulley into the wheel, like that. Put the wheel in from the side, through the gear, out the other side. On the other side we can put another wheel and pulley. We can do the same for the front. Then we can add the motor by looking at the dimensions between the holes of the motor and the dimension of the diameter of the hole. Put fasteners through to keep the motor in place. Put the little gear on based on the shaft diameter and the diameter of the hole inside of the gear. And put the little elastic bands over the pulleys for the four-wheel drive feature. So now that the assembly is done, you can make a drawing of it. Typically, you will assemble this whole thing in your head. So you will think, okay, I put this there, I put that there, that's what it's going to look like. Do it in your head, and then after that, you make an assembly drawing of the entire thing. Okay, so that was basically the lecture for today. Are there any questions? If your head does not have enough RAM, what you can always do is you can, on a scrap piece of paper, make yourself some basic sketches. For example, okay, there we have the pulley. Next to it, we have the wheel. Then you can make use of basic hand sketches, and then you can indicate where it should go, and then from there you can do the final assembly drawing.